Okay, we're going to talk about MANOVA, multivariate analysis of variance. So what is multivariate? There are three categories of analysis to be aware of. Univariate analysis, which looks at just one variable, bivariate analysis, which analyzes two variables, and then multivariate analysis, which looks at more than two variables. Multivariate analysis encompasses all statistical techniques that are used to analyze more than two variables at once. The aim is to find patterns and correlations between several variables simultaneously, allowing for a much deeper, more complex understanding of a given scenario than you'll get with bivariate analysis. So MANOVA allows us to look for differences across several dependent variables at the same time. You need to look at the linear combination of two or more dependent variables to see if there are differences across your independent variables. There are, as with all of our statistics, some assumptions. The first is that two or more dependent variables are measured at scale level, meaning their interval or ratio. At least one independent variable that must have two or more categorical groups. Observations need to be independent, and you need to have an adequate sample size. You can use G-power to determine adequate sample size. Here's a little snip. You go to the F-test, and you can start with the global effects. MANOVAs assume multivariate normality. They're sensitive to outliers. There needs to be a linear relationship between each pair of dependent variables across each level of the independent variables. You need to have homogeneity of covariance matrices, and the dependent variables cannot be multi-collinear, which means too highly correlated with each other. So here's a scenario. The CEO of a major hospital system wanted to know whether there were differences in inpatient satisfaction ratings and their perceptions of affordable service among patients at three large urban hospitals. As such, she randomly selected 20 patient ratings from Hospital A, 20 ratings from Hospital B, and 20 from Hospital C, and measured their inpatient satisfaction ratings and their perceptions of affordable service as assessed by a survey. These two scores served as the dependent variables and were labeled satisfaction score and affordable score, respectively. The independent variable was the hospital where the patients were surveyed, and that was labeled hospital. So let's test the first assumption. First, we'll check for multivariate outliers, and we need to use linear regression to test each independent variable separately. So we go to Analyze Linear Regression, move subject ID to the dependent variable, and the DVs to the independent variable box, and click Save. So we'll bring subject ID over to the dependent variable. We bring satisfaction score and affordable score over to the independent variable and click Save. All we want to check is this Mahalanobis distance. And we click that, click Continue, and OK. So you need to look at the maximum allowable value of Mahalanobis distance. It depends on the number of dependent variables you have, and here we have two DVs, and our max here is 5.3. So what's the cut point? I have two predictors, the dependent variables being used as independent variables in the regression. So I have two numbers of DVs, so my critical value is 13.82. This is less than that, so we do not exceed it and say that there are no outliers. Okay, so now we're going to make scatter plots. We need to test the linear relationship among variables. The easiest way to do this is to go to Graphs, Legacy Dialogs, Matrix, Scatter. Move the independent variable over here to Rows, and the dependent variable to the matrix variable, so up here. Click Options, right here, and click Exclude Cases Variable by Variable. Click Continue, and then click OK. That's just in case you have missing data. We don't, but I want to show you that. Okay, so you're looking for a linear relationship. This is subjective, but we're going to call this linear. Mostly this one, this one, this one, maybe not so much these here, but we're going to go for it. So then we want to check the normality of the dependent variables. So this is not the same as multivariate normality, but we'll check the normality of the dependent variables. So you move over your variables, Analyze, Descriptives, Explore, Normality Plots with Tests, click OK. We've done this before. Uncheck the stem and leaf. And then we see that we have all normal distributed among the hospitals in each level of the dependent variable. Okay, now we want to check for multi-collinearity. This is when you have strong correlation between the dependent variables. Anything over 0.9 is considered problematic. We check by running bivariate correlations among the dependent variables. Here we're okay, we don't have a large correlation, we only have 0.39. All right. Now we're ready for the actual MANOVA. So we're going to analyze, general, linear, and model, and now we're using the multivariate tab. So we move over our variables. We've got fixed factors, hospital, satisfaction, and affordable score, and we're going to click post hoc. Since our independent variable is 3 levels, we need post hoc tests or contrast. We will use post hoc tests. Click continue and then click options. So we click Bonferroni and continue. Select the following options and then continue and then OK. So we want descriptives, estimates of effect size, and homogeneity tests. Okay, so the important row in the table below is the sig row here. That's in the red rectangle, which represents the significance level, the p-value of the test. For this test, the recommended alpha level is p is less than 0.001. So if this test is statistically significant less than 0.001, you have violated the assumption of homogeneity of variance covariance matrices. If the test is not statistically significant, i.e. it's over 0.001, you have a homogeneity of those variance covariance matrices, and you haven't violated the assumption. In this example, the sig is greater than 0.001, it is here 0.003, which indicates that we've met this assumption. Here we're going to just go look at the Levine's test, and we see that we have equal variances for both scores across each level of the independent variable. We get close here and we get close here, but they're not significant, so we say equal variances. And then we want to evaluate the output. So examining the descriptives, we see that Hospital A has higher scores in both satisfaction and affordability than Hospitals B and then Hospital C, so it's consistently higher. If all the assumptions have been met, we'd select the Wilks lambda and use that p-value. Although Wilks lambda is usually recommended, Pillai's trace is more robust and is recommended when you have unequal sample sizes and also have a statistically significant boxes m-test result. We see that our p-value is less than 0.001, so we're going to use Wilks, where we see that we have 0.001, and so we report there was a statistically significant difference between the hospitals on the combined independent variables, and we report it out. This is a upside down b is a lambda in Greek. Partial eta squared, which we've asked for, is 0.387. And then we can look at these tests of between subjects effects, which is univariate one-way ANOVAs, to determine which dependent variable would appear to be contributing to the statistically significant MANOVA. We can see that the satisfaction score was significant and the affordable score was significant for hospitals. So then we look at our post hoc test, and I've just highlighted all of the significant comparisons, but only a few of these are needed. So we're looking first inside the satisfaction score, and we see that Hospital A and B are different, Hospital A and C are different, and then we want to know, is Hospital B and C different, and we see that they're not. All right, so then we look at the affordable score, and we see that Hospital A and B are not different, Hospital A and C are different. Hospital B and A, we've already looked at that one. Hospital B and C are different, and then Hospital A and C are different than both. So multivariate analysis of covariance, or MANCOVA, is just like ANCOVA, but with 2 dependent variables. The one-way and multivariate analysis of covariance, one-way MANCOVA, can be thought of as an extension of the one-way MANOVA to incorporate a continuous covariate, or an extension of the one-way ANCOVA to incorporate multiple dependent variables. This covariate is linearly related to the dependent variables, and its inclusion into the analysis can increase the ability to detect differences between groups of a categorical independent variable. A one-way MANCOVA is used to determine whether there are any statistically significant differences between the adjusted means of 2 or more independent unrelated groups having controlled for a continuous covariate. You need a reason to use MANCOVA. Do you have some empirical or theoretical reason why the dependent variables should be treated together? Just clumping together many variables because they were all measured is generally not considered a good idea. Are you interested in the effect of each dependent variable or only their effect as a whole? For example, you've measured a number of types of motivation. For example, extrinsic motivation, intrinsic motivation, etc. but are only concerned with overall motivation. If you're only interested in the effect of the dependent variables as a whole, you might consider the dependent variables jointly. Okay, like with everything, we have some assumptions. The first is that two or more dependent variables are measured at scale level, so that's interval or ratio. At least one independent variable that must have two or more categorical groups, one covariate that's continuous. Observations need to be independent and you need to have adequate sample size. MANCOVAs assume multivariate normality. It's sensitive to outliers. There needs to be a linear relationship between each pair of the dependent variables across each level of the independent variables. You need to have homogeneity of regression slopes, and the dependent variables cannot be multi-collinear. A researcher wanted to determine whether cardiovascular health was better for normal weight individuals with higher levels of physical activity, as opposed to more overweight individuals with lower physical activity levels. As such, the researcher recruited 120 participants who were subsequently divided into one of three groups, depending on the amount of physical activity they performed. A group who were classified as engaging in a low amount of physical activity, a group who were classified as engaging in a moderate amount of physical activity, and a group who were classified as engaging in a high amount of physical activity. There were 40 participants in each group. In order to measure cardiovascular health, the researcher took three measurements from participants: cholesterol concentration, C-reactive protein, and systolic blood pressure. The researcher expected that increased levels of physical activity would have an overall beneficial effect on cardiovascular health as measured by cholesterol concentration, C-reactive protein, and systolic blood pressure. However, the researcher understood that body weight would also affect these three measures of cardiovascular health. As such, the researcher wanted to control for differences in body weight of participants. Therefore, the researcher ran a one-way MANCOVA with cholesterol concentration, C-reactive protein, and systolic blood pressure as the dependent variables, body weight as the continuous covariate weight, and three physical activity groups, low, moderate, and high, as groups of the independent variable. Okay, so here we have the data, we have group, we have cholesterol, CRP, SBP, and then weight is our covariate. And our independent variables, low, medium, and high. So the first thing we want to check is homogeneity of regression slope. So we put our dependent variables in the dependent variable box after we've selected analyze, general linear model, multivariate, and we put in cholesterol, CRP, SBP, and we have our fixed factor as the grouping variable and weight is our covariate. We come over here, we click model, and we click build terms. We bring group over, then weight over, then hold down shift and have the interaction. Click it, and we see that group times weight is the interaction term. Click continue. We can see here that in the group times weight interaction term, none of these are significant, so therefore we have homogeneity of regression slopes. So to save time and effort here, I'll just report the output of the MANCOVA. The steps are the same as MANOVA described above, but with the addition of the covariate. So we look at the Mahalanobis distance. I'd have to run that using linear regression, and I can see that my maximum is 11.4. When you have three dependent variables, the maximum you can have, the cut point is 16.2, so we don't exceed that, therefore we have no outliers. Here we can see the descriptive statistics, and we don't have significance for boxes test here, so we have equal covariance matrices. So we go to our multivariate test, and we can see, looking at Wilks lambda, that we have significant differences for the group. There was a statistically significant difference between the physical activity groups and the combined dependent variables after controlling for weight, and we report out the Wilks. We look at the univariate test, and we see that for the cholesterol across the groups, C-reactive protein, and systolic, there were significant differences. So if the one-way MANCOVA is statistically significant, this suggests that there is a statistically significant adjusted mean difference between the groups of the independent variable in terms of the combined dependent variable, i.e. after adjusting for the continuous covariate. Follow-up univariate one-way MANCOVAs were performed. There were statistically significant differences in adjusted means for cholesterol concentration, and I report out this F statistic, C-reactive protein, and this F statistic, and systolic blood pressure. You can look at the pairwise comparisons. I have highlighted the ones here. You can see what's significantly different. And then I'm not going to read this all, but copy this and paste it into your own study if you're going to use a MANCOVA, and you can change the variables to fit your own reporting.